So we're going to talk about chemical reactions involving oxidation and reduction. So this type of chemical reaction involves the transfer of electrons. And so if electrons are moving, we should be able to harness some electricity, but I think my battery's dead. Another purpose for studying oxidation reduction reactions is to think about how on a very large scale we do mining. We mine our planet to find ores, iron ores, or other metal ores, and then we like to use that metal, so we have to get rid of the coatings, the oxide and sulfide coatings. And so this happens through oxidation and reduction. So we think about iron oxide, which is just a common type of iron ore, iron 3 oxide. We could eliminate this oxygen coating, this oxide coating, and get bare iron metal if we react it with some carbon monoxide. So we just take this gas and pass it over there, and it really needs a lot of temperature, and we can essentially take this iron 3 oxide and just kind of get rid of that coating, like reduce the coating. So this is a reduction process. The iron oxide is undergoing a reduction process. It loses oxygen. And so where's the oxygen go? It has to go somewhere. Well, it takes this carbon monoxide here is becoming carbon dioxide in this balanced chemical reaction. So that's where the oxygen's going. And so we call this sort of process that the carbon monoxide is undergoing, we call it oxidation. Because it sounds like oxygen. It's gaining oxygen. So it's like this process of reduction and this process of oxidation. It's like two halves of the whole thing. Well, here it sounds like this whole transfer of oxygen is going on. So we can add some other terms. We can say this carbon monoxide is chosen to bubble over this metal ore here because it acts as a good reducing agent. An agent causes change. So this kind of reducing agent is causing reduction. So in itself gets oxidized. So if you want to do it from the perspective of the iron oxide, you might refer to that as the oxidizing agent in the situation. Agent causes change. It's causing the oxidation of the carbon monoxide. So in the process, if it's supplying oxygen, it's going to get reduced. Now, we know that all oxidation reduction reactions involve a transfer of electrons, but not all of them involve oxygen. Like this one, we can clearly see how the oxygen is being transferred. I want to be able to talk about how electrons are transferred, but let me show you an example where we're not talking about any oxygen at all, and instead we want to think about reduction with respect to a charge, right? Because electrons have a negative charge. So if we want to think about where they're moving, that's going to change the charge of different species. So let's think about this example. If you were to have a solution with silver ion in it, like a silver nitrate solution, and you drop some wonderful orange copper metal in that aqueous solution, these two things will react. And in fact, what you'll start to see is some really nice silver metal being produced, and then the orange copper solid goes away, and instead we get a blue copper +2 aqueous solution. And the balance here happens to be like 2 and 2. So let's think about this. If we think about silver +1 over here, this silver has no charge at all. So you could put like a 0 there. The charge that's changing is each one of these, the +1 is going down to a 0. So we'd say this process here is a reduction in charge. Reduction in charge. And the only way to reduce from a positive down to a 0 is to gain a negative. Gain a negative electron. So each silver gains a negative electron. We got 2 silvers here. Where do they come from? Well, they have to come from the copper. That's what's reacting. These two things are reacting. So copper, which starts out as just as neutral copper, like copper 0, it's actually becoming, right, changing into, oh, copper 2 plus, that's electron deficient. So we're going to call this process oxidation. Yeah, I know there's no oxygen involved, but the term continues because we think about it as the opposite of reduction. So oxidation here, to go from a 0 up to a +2, involves the loss of negative charge. So then we can add some terms here. We can say the copper itself is a reducing agent. The agent causes the reduction of the other species, and in the process gets oxidized. And then the silver +1 ion, from that perspective, you can think, oh, we'll call this thing the oxidizing agent because it's causing the oxidizing of the other species. The oxidizing agent gets reduced. So now we see a transfer of electrons here, not a transfer of oxygen. So let's go back to the original example. Do we have a transfer of electrons? Let's look at the reduction. We should see a reduction in charge. All right, so this is an ionic compound, iron 3 oxide. We know that that metal there has a +3 charge. Each of those irons has a +3 charge. Oh, here, no charge at all. There's our reduction in charge from a +3 down to a 0. Great. Now let's see the oxidation. We know the oxidation is a loss of electrons. Reduction in charge is a gain of electrons, and oxidation is just the opposite. So let's see, can we track the loss of electrons? Well, carbon monoxide, oh, that's a molecular compound. This was ionic. We know that iron has a +3 charge there because that's what the Roman numeral is telling us. But here, I don't have any charges. These are shared electrons. And over here, molecular compounds, shared electrons. What are we going to do? How can we assess the loss of electrons here? Well, we need some way to do it because the electrons that this compound is gaining through the iron has to come from somewhere. It has to come from here. There's going to be a loss of electrons. So where's it coming from? Well, we'll have to make up a paradigm that will help us figure out what kind of charge here. And we're not going to call it charge. We're going to call it an oxidation number because we're having trouble assessing this oxidation process. So do you have the little sheet here? This is going to help us. What are we going to do with this? Well, we're going to come up with a method here according to these rules to help us keep track of electrons, where the method is just, we're making it up. It's artificial, it's formal, and it's really going to help us with things like molecular compounds, carbon monoxide and carbon dioxide, or even molecular ions. So oxidation numbers themselves, they're a kind of charge to help us with redox, but they're fake, a pseudo charge. And we just have 4 rules to think about. So this little handout, let's talk about these rules if you have your handout. We're going to assign, this is how we assign pseudo charges to each element within a compound. So groups 1 and group 2 and transition metal cations, like iron +3, its oxidation number that gets assigned is the typical charge that it has. Okay, that's easy. If you have a pure element, like just plain old iron, or if you have like oxygen, diatomic oxygen, its oxidation number is just 0. Now, these are really helpful. Things like oxygen, here's its oxidation number, hydrogen, and fluorine. Those are really, really helpful. And a couple of exceptions here. And then the last thing is there's a lot of other elements. So to figure out what the oxidation number is for all other elements, we need to follow this. Let's see. Let's apply this. I've got some things about a compound and an ion. So I have 2 compound examples and an ion example. Let's assign the oxidation number for each element within this compound. So hydrogen. Hydrogen is assigned a +1 unless it's with a metal hydride like sodium hydride. Oh, then it would be an anion. Okay, so it's not. And then oxygen. Oxygen is assigned -2 unless it's with a peroxide. No, there's no peroxide here. This is a sulfate within sulfuric acid. Okay, I got another element here, sulfur. But there's no sulfur here. Oh, but I'm going to use this rule. The sum of the oxidation numbers, that's for each element in this compound, has to add up to 0. So let's see, a hydrogen is +1, but I have 2 of them. 2 of these +1s, I'm going to sum it. A sulfur, I don't know what that is yet, plus 4 of these -2s, that's the oxygen, has to add up to 0. Right, so 2 plus sulfur minus 8 equals 0. That means your sulfur, this sulfur, whosever sulfur it is, has to be equal to a +6. So +6. So here's our answer. This is assigning the oxidation number to each element in that compound. Let's try this one. We got potassium. Oh, potassium's group 1. Its oxidation number is going to be +1. Group 1 +1. There's an oxygen again, -2. My other element here is chlorine. I don't know what to assign that. I don't have a rule for chlorine. But I do have this. The sum of the oxidation numbers has to add up to 0 for a compound. So let's do that work. Potassium is +1. I'm going to sum that with chlorine. I don't know what it is, so I'll just leave it as Cl. And then I have 3 of these -2 oxygens, sums up to 0. So if we do our algebra here, we see that our chlorine has to be a +5. +6 minus 6 equals 0. There, so we did that one. And let's try that. Okay, now here we have carbonate ion. So when we sum up the oxidation numbers, they're going to have to add up to the charge of the ion, which is -2. Oh, I've got an oxygen. Oxygen is in -2. Got to figure out what the carbon is. So carbon plus 3 of these -2 oxygens has to sum up, not 0, sum it up to -2. Yeah. So our carbon has to be a +4. Carbon's +4 because here 4 minus 6 equals -2. That's great. So that gives us a very straightforward method for assigning oxidation numbers. I think we're ready to go back to our original example here and figure out. Well, here's carbon monoxide. Let's see, carbon with a -2. I'm sorry, oxygen with a -2. What do we put for the carbon? Well, they have to sum up to 0, so that means the carbon is a +2 here. But over here in carbon dioxide, okay, oxygen is a -2, but we have 2 of them. So what should the carbon be? Right, it's got to be +4. So we go from a +2 of this element within carbon monoxide to a +4 of carbon within carbon dioxide. +2 to +4. Yes. That is definitely an increase in positive charge, which means it's losing negative. Look at that. Oxidation increases charge. Reduction, that reduces charge. That was from the +3 on the iron down to 0. So redox, in summary, how do we remember the definitions of these terms? Well, I like to think of just the reduction part. Reduction is the gain of electrons. Why? Because it's reducing the oxidation number, the charge, +3 down to 0. If you memorize that one, reduction in charge, then you know the other one. Oxidation is just the opposite. Sometimes people use these mnemonic devices. Oil rig, oxidation is loss of electrons, reduction is gain of electrons, or like Leo the lion, loss of electrons is oxidation. It's your choice. I just like to think, oh, reduction is a reduction in the oxidation number, reducing the charge, decreasing it. You can only do that by adding some negative. So with your group, it would be good to practice these things. So right now you can pause the video and you can try these 2 quick questions and talk about it with the group. And you want to turn that in by the end of class. Otherwise, this is the end of the video.